Morning, everyone. So I'm going to talk a little bit about risk when it comes to climate change. So we're all in the business of managing climate risk. Humans have always been in the business of managing climate risk. The first climate model is a calendar, basically, that allows you to plot the changing seasons, plan your crops or plan your foraging. It's basically a model for solar-driven variability in the climate system. It's not a new science, it's a very old science. But these days we're managing more than that. So the change in the atmospheric composition has introduced a new element to climate risk, and that's a large theme of this conference obviously going forward. So climate change is happening now. I've just drawn this little table here of things that are happening at the moment and things that are emerging. So for Australia, obviously increased frequency of large-scale heat waves and record high temperatures, something that is impacting on the continent now. It's impacting on urban populations, it's impacting on rural populations, it's impacting on ecosystems across the continent. We've got a longer fire season, so there's more extreme fire days during that season. It pushes further into spring and autumn, and the most severe fire weather danger days are getting more severe during that period. We've also got prolonged high ocean temperatures, so Leslie talked about the back-to-back bleaching on the Great Barrier Reef, and I'll come back to that example later in the talk. Emerging is also more time spent in drought globally, as well as in Australia. A great proportion of rainfall coming from heavy rainfall events. So as the planet warms up, the atmosphere can hold more water, the oceans pump more water into that atmosphere, so your rainfall rates go up quite dramatically. And the big one that is going to impact on not just Australia but our region, every mega delta from Korea through to Pakistan, is the increased frequency of coastal storm surge inundation with sea level rise. So the challenges are significant. This is what climate change looks like when matched to population pressure, when matched to inappropriate governance potentially. So the picture at the top there is the Waterscliff Dam, which is to the west of Cape Town. It's looking very dry, as you can see right now. It is part of the Western Cape water supply system, which is a very extensive engineering works to supply water to Cape Town. What you can see in the bottom there is people queuing up. So for people that don't know, Cape Town was approaching day zero, which is the day that they ran out of water in that Western Cape water supply system. They've pushed that back largely by going to quite severe water restrictions. So I think something between 15 or 25 litres of water a day. So obviously that's something that most managers, asset managers, governments don't want to see, people in Australia don't want to see, and that's the challenge that we have. So looking at that graph there, that is the water available in the dam, and you can see it's been going down steadily since 2013. Looking at the rainfall data, so I've got a few graphs there. It's hard to see a trend, that's because rainfall is quite difficult to see a trend, but you can see prior to the 1980s, you've got some quite high rainfall years, tailing off in the last 2 decades with some low rainfall years and a loss of those really wetting periods. So as well as impacting on the urban supplies, you've now got basically no water for agriculture right around that region. And I don't know if my mouse works or not. The dam's over here, Cape Town's here, you've got the ranges in between, but largely agriculture in this region stopped. The map there on the right is rainfall trends globally, and you can see these brown patches, if you just focus on the southern hemisphere, kind of in a latitude ring around the continent, around the globe, around the hemisphere. The western-facing capes, or western-facing coasts of Chile, Australia and Southern Africa all have this rainfall decline. As the tropics are expanding, we're pushing the frontal systems that brought rainfall to these parts of the world further south, so it's still raining, it's raining over the Southern Ocean. Not over those land areas. So that's something we're dealing with right around the hemisphere. Here's a picture from Lake Hume in 2007 during the Millennium Drought. So dry dams aren't something that are foreign to Australians, obviously. But it is actually, if I've got one positive message today, we do quite a good job of managing our water resources in Australia. So if you can remember that graph from the Western Cape, the top graph there is from southwest WA. So there's less rainfall in southwest WA on an annual basis, and the rainfall decline is actually more severe than it is in South Africa. Again, you can see prior to 1970s, those high rainfall years. So this was about the most reliable wintertime rainfall in the country. It has an ecological niche similar to the Eucalyptus regnans, the mountain ash in the southeast. It's got the Carrion Marri forest, obviously wet for millennia. The Calitris, so the tree ring species show that drought periods are probably no more than about 20 years. So it's been about 40 years now with this rainfall decline. That decline in rainfall, about 25%, matches through to about a 60% drop in streamflow as the soils and the vegetation get drier. So that's what's happened in South Africa. It's what's happened here as well. What I've got there is 1997, we started the IOC Research Partnership, so the Indian Ocean Climate Initiative, the WA government, CSIRO, BOM and others. And that is evidence of what happens when you target research in the right place and start it at the right time. So it's resulted in a number of policy outcomes in the southwest, desalination plants. There's 2 that are built. There's probably another one that will be built, maybe another 2 before we're done. Sewage reclamation, recharging the groundwater, for example. We've had a similar rainfall decline in the southeast, but it's been more recent. We're a bit further south. We get rainfall from other directions. But again, it's really the loss of those cold fronts and cut-off lows. The SEACI partnership, which is something that's a bit more familiar to those in the southern Murray-Darling Basin. Quite a lot of state governments and water authorities and BOM and CSIRO were involved in that. And again, the outcome there was to understand what was driving those rainfall declines. IOC was named that because we didn't know what was causing that rainfall decline. We thought it could be something off the Indian Ocean, but it turns out that it is greenhouse gases. It's a long-term decline. And again, we have some sort of a roadmap for the southeast in terms of what we do to decouple our water security from the climate system itself. So just to underscore the challenge that we've still got in front of us and that we're not actually meeting, nothing really demonstrates that better than future sea levels. So the lead times you need to plan research, to design outcomes and to implement policy are quite long. Sea level, so coastal ecosystems are squeezed from both ends. So we're having rising seas, increasing storm surge inundation and increasing urbanisation from the other side. And eventually that rising sea will actually impact on those assets at the coastal level, and that's right around Australia and regionally, obviously. That's an inundation map for Adelaide at 2100 under a high emission scenario. It's one of the less dramatic places in the country. I could have shown Cairns where the whole city is underwater for a storm surge later this century, for example. So the salient things from that is that it takes a long time to plan and build sea level defences. If you look at the Thames Barrage, it's probably a 3-decade build from designing it through to completion. So really, if we are going to protect the harbours and bays of our cities now, if we're going to barrage, say, Port Phillip Heads or Sydney Harbour, those engineering works and scoping works should have started already, and they haven't. So that's a long lead time, but we are capable of doing those sorts of things. So, for example, submarines take a long time to build. They'll be ready by 2050. So we do look to that kind of a horizon for when we undertake these kinds of works. So compound extreme events are the things that are going to get us, and my talk today is a little bit about what that means for understanding risk. So not so long ago we were just talking about a median, so a mid-level emissions scenario, the mid of the pack, not the high-end models that are producing quite a lot of climate sensitivity, not the low-end ones. We'd go with one variable, maybe rainfall or temperature, and we'd try and determine risk off those. In a very short space of time, over 5 years, as the finance system and other places have understood that they're exposed to this climate risk, they've asked the science to actually give them the worst case scenario so that they can stress test whatever it is. It's an operational system, might be a bit of critical infrastructure, it might be a natural asset. That rapid shift has the science not quite ready to actually produce that, and I'll demonstrate that in the next few slides. But it's the compound extremes, it's those ones where you get different extremes of different duration and different variables all interacting with each other. So it's a long-term rainfall decline coupled with a few years of high temperatures, coupled with an intense heat wave, coupled with a short, really intense drought, for example. We don't normally go looking for those sorts of things in climate models. We need to know the vulnerability first if we're going to crank up a supercomputer and actually get really high resolution impacts out of the models to actually do that. And a lot of that mapping hasn't actually been done. So I've got an example here from Tasmania across 2015 and 2016. It's a little vignette of climate change through the eyes of a compound extreme event. So what's going on in the background? We know that spring is getting warmer across the country. So the orange on the map there on the right is highest on record temperatures. Across 2012 to 2015, the 3 hottest springs on record occurred in Australia, all adjacent to each other. So there's a warming trend. There's also an increase in fire danger. So the bottom map there is the Forest Fire Danger Index. It's a measure of how quickly a fire spreads, so whether conducive to fire. We know that that's happening in the background as well. And it's not just the scientists that know that, it's also natural resource managers, fire managers, emergency services, water managers. Everyone's aware of these trends. Southern Australia's been drier, as I've already talked about. So the rainfall maps there show it's been mostly in the cool season where we've lost rainfall, but for Tasmania it's actually been in both seasons. That's because they're impacted by those frontal systems not just in the winter but in summer as well, so they've lost their rainfall year round. You can see the past 20 years lowest on record for the western half of the state there. And looking over the 2015-16 period, we were on trend, so you don't need to be on trend. If you look at the bottom graph there, looking at rainfall, there are some years where the rainfall will still be high. It's just that we've got a background trend of reducing rainfall. And over this period, 2-year period, we were basically consistent with those trends. That map looks pretty much like the trend map, just for that 2-year period. So what happens when this trend meets weather? So leading into, so as this situation developed, an El Nino developed in the Pacific across 2015. That normally brings drier and hotter temperatures to Eastern Australia, sometimes to Tasmania. When you combine it with the trend, it's not just hotter and drier, it's sometimes at the extreme end. So for October 2015, combined with an El Nino, combined with that background trend, we had the hottest October on record, the driest October on record, and the most severe fire weather on record for that period, all intersecting with each other. It's generally during these periods that unusual things happen, such as fire in old-growth wet forest that hasn't occurred maybe ever over the life of that forest on the scale that we've seen it. There's human decisions going on. So we went into this period with low hydro storages across Hydro Tas. Over this summer, the interconnector connecting electricity from Tasmania to Victoria failed. So we were importing diesel generators over from the mainland to back up the electricity supply during this event. So that's a compound event. What happened next is we went to flood. So not just any flood, probably the worst flood, or almost certainly the worst flood that northern Tasmania has seen, certainly over the record-keeping period. That switch from drought to flood is definitely something that the models have long said would happen, particularly in the Pacific. So when we're talking about those Pacific islands, that disruption to their rainfall pattern and the sequencing of extreme events is something that's really going to impact. In terms of, and if you're talking risk and stress testing, what's going to break a system, it's that sequence, and it's whether we're actually properly characterising that risk right now to understand that. So again, looking at this rainfall, what was going on in the background? In May 2016, so just before the month just before the week of that rainfall, the orange there is highest on record sea surface temperatures, and as I said at the start, warm seas provides moisture into the atmosphere and increased rainfall rate. So how warm was it in the Tasman Sea? You can see over the right here, it wasn't just a little bit above the previous record, it was about double. Now, if you look in a climate model, you have to do quite a lot of individual climate model simulations to actually come up with something that looks that dramatic. It's not something that pops out straight away. So that's really salient again, is if we're properly characterising our risk space, if we're going to the models to determine it rather than to the vulnerability, you're probably going to underdo it. So keeping your eye on that warm water, we had an east coast low sit just above that region. That means that the winds are channeling in this northeasterly direction, picking up all that moisture and dumping it onto the New South Wales and Tasmanian coast. So subtropical moisture along New South Wales isn't necessarily unusual, even at that time of year. It was a compound event, so it was also a high sea level event as it was pushing that water up along the coast. So that was that famous picture from Collaroy Beach where someone's pool fell into the foreshore there. But for northern Tasmania, it's really unusual. So when we looked above Hobart Airport during this event, the amount of water in the atmosphere was about 40% above the previous daily record. So again, that massive jump isn't necessarily something you're gleaning from the climate model space at all. We had 5 rivers in flood. picking up freshwater crays and depositing them over paddocks, essentially right across northern Tasmania. That's Cataract Gorge. I don't know if people are familiar with what that looks like normally. It doesn't look like that. That looks like an Alaskan glacier melt or something else. But yeah, it's quite an extreme outcome. So what can we do to construct these events? Well, as I said, you're not necessarily led there by the models, but you are led there by your vulnerability. So I'm just going to show an example from the Great Barrier Reef where we possibly don't even need to go to a climate model at all if we properly understand the vulnerability that we're dealing with. And when it comes to the reef ecologists have done a fantastic job of understanding that. So they can hand the climate scientists a really neat set of vulnerabilities such as thermal stress, craniophylline starfish, which is increased by sedimentation, tropical cyclones. So we have this whole gamut that we can put together in a cumulative sense, and it actually just takes someone expert in weather to put that together in a plausible way that potentially antagonises the vulnerabilities that we're talking about. So sea surface temperatures during that back-to-back bleaching period, 2015-16, it wasn't just the Tasman, it was the whole north of Australia that was warmest on record. Again, you can see it wasn't just a little bit above, it was quite a jump previously. These are degree heating days, so it's accumulation of positive heat anomalies over the reef. And you can see what happened in the 3 years. The bleaching occurred in 2015, 2016, 2017, 2018. Again, if you went to a climate model, you wouldn't find back-to-back bleaching on the reef. In fact, you wouldn't even resolve this. It doesn't resolve weather at that scale. You would need to run a nested weather model inside the climate model, both in the ocean and the atmosphere. Again, that's a supercomputing task. You wouldn't just do that randomly. You need to understand your vulnerability before you undertake an exercise like that. But that's what we're dealing with. So having actually experienced that and experiencing what it actually did to the reef, we can ask ourselves a series of questions. So this is the last graph I'm showing, but what it is temperatures over the Coral Sea from December through to April, and you can see it rises over summer. In those years where we have an El Nino, where we have a lack of cloud cover over the late February, March period, the temperature peaks then, and that's typically when you get your bleaching events. Looking at those back-to-back bleaching years, they are well above the pack. So this is the 1900 to 1930 average for the temperature curve. This is your average El Nino event in dotted lines there, and the dashed line there is your average from 1900 to 2016. So we're way above the pack there, and the question would be, well, that was what happened in 2015, 2016. What's the likelihood that we get 3 years in a row? It turns out that's quite plausible if you consider an El Nino, La Nina cycle. You could get 3 years of those bleaching events in a row, and it could happen in the next 10 years, really. And what happens if we get those events followed by a tropical cyclone that makes its way all the way down the reef? That's a real tropical cyclone. That's Tropical Cyclone Hamish in 2009. And following an event like that, the mechanical damage on the reef, and then probably flooding and sediment flush into the reef compounds that event again. And we can actually construct an event like that just based on the vulnerability and the knowledge of our weather. So that's kind of where we're probably going to go now. We see overseas they're a little bit more mature in this area than us. They are stress testing a range of natural and built systems for these compound extreme events, but we are just starting that in Australia. So I'll be around for the rest of the day if someone wants to ping me on what we can do in this space as Bureau and CSIRO science providers. It is an interesting area. Thank you.